It's 8th week, Friday. That's great. Just a couple more weeks left, and then it's summer break. Maybe well, I'll be here during the summer, but maybe you will get to enjoy some time off, or maybe you're working. Also exciting. Okay, let me just give kind of a brief overview of what's happening with the rest of this class, just so you can kind of, I don't know, think about it. All right, so today I'm going to wrap up chapter 8, okay? And then next week is week 9, and we will cover chapter 9, okay? You'll have a quiz which covers chapter 8 on Tuesday, but I'll be covering chapter 9. And then week 10, we will spend mostly doing review, okay? Review and kind of, I just want to make sure I've hit all the conceptual points on statistical inference. So it'll be like statistical inference, I don't know, catch-all. Okay, so I'll cover all of that in week 10, and then week 11, I don't know if it's fair to call it week 11, the final exam. It's going to be about 80%-ish, 80% chapters 7, 8, and 9, and then about 20% basically chapters 1 through 6, okay? And the chapter 1 through 6 stuff is going to be mostly conceptual. So ask mostly conceptual questions from chapters 1 through 6. You don't need to worry about, I don't know, doing complicated calculations for chapters 1 through 6. Okay. All right. I think that's good. And I know these last few weeks can be stressful, but again, the worst possible thing ever that can happen is like you fail all your classes. Okay, that's like the worst ever, and it sounds pretty terrible. Okay, it sounds terrible, but in the grand scheme of things, it's not that terrible. Okay, there was a quarter where I failed all of my classes, and I was like really sad, but I'm okay. So I have my dream job now, you know. So like, you know, you fail all of your classes, life goes on. You'll be fine. Okay, don't freak out too much. Okay, that's like the worst possible thing, and it sucks when you're going through it, but you know, it's okay. All right. So don't worry. It's just classes. All right. Okay. So let's talk about chapter 8. Oh, let's do a review question. Okay. So we'll do a clicker question. Where did my clicker thing go? I like having clickers. I'm sorry that the clicker remotes are so expensive. And they have something like you can use your cell phones to do it, and that would be great. Except they all charge you they charge you just as much to use the silly app on your phone as like purchasing a clicker. There's like another company, and they keep sending me emails saying like, try this. Students can use their own cell phones, and I'm like, oh, let's see. Oh, you're going to charge the exact same amount. It's like, yeah, no, thank you. Everyone just wants your money. So, okay, all right. Anyway, all right. Okay, so let's say this is on type 1 and type 2 error. Okay, So if you recall, type 1 is like the false positive, type 1 error versus type 2 error. Okay, so we're going to see, so let's say you perform a hypothesis test to see if the proportion of cat owners in the population is over 30%. Okay? So at this point, you should be thinking, what are the hypotheses, right? What hypotheses are you using? Okay. And then, okay, so then based on your data, okay, you decide that you do not have evidence that the proportion of cat owners in the population is over 30%, okay? And then, but in reality, the proportion of cat owners is 34%, okay? All right, so what is this? So A is type 1 error. B is type 2 error. And C would be correct conclusion. Okay, go ahead and get your clicks in. So try to figure out what the hypotheses are and what your conclusion was, and whether you have made the right or wrong conclusion, and what kind of error that is. Okay. So I'll tell, while you guys are figuring out what button to click, I'll tell you a story from that quarter. I failed all of my classes. Well, I did get a D in one of the classes, so I didn't fail. I guess I didn't fail all of them. And they're like, the report cards were a little bit different from here, where you just kind of bubble in A or B or whatever. One of the professors wrote. And I kept this one because it was so, like, it felt so personally mean. He wrote Miles was the weakest was the weakest student in the class, and I was like, oh man, that's kind of harsh to write. It was very sad. Because I don't know. He was like, Miles was the weakest student in the class. I was like, man, that's kind of mean. But anyway, I kept that one. So that was the quarter I failed, but yeah, anyway. Okay, so what do we have? We got, are we done clicking here? Can I, all right, I'm going to go ahead and click stop. Let's look at this. All right, okay, well, at least we are in agreement that number C is not the correct one. Okay, all right. So this is the tough one. Okay, so it says you're performing a hypothesis test to see if the proportion of cat owners in the population is over 30%. So here, our null hypothesis should be what? That the proportion is 30%, and then the alternative will be that the proportion is greater than 30%. Okay, are we in agreement there? Okay, so based on your data, you decide, so our conclusion is that you do not have evidence that the proportion of cat owners in the population is over 30%. Okay, so this sounds like we rejected or didn't reject the null. So here, so our conclusion is do not reject the null. Okay, and in reality, the proportion of cat owners is 34%. So the truth is that P is greater than 0.3. Okay, so the truth is that the proportion is 34%, meaning that P is greater than 0.3. So that means the null hypothesis is false. Okay, so if the null is false and we did not reject the null, that would be type 2 error. Okay. All right. So 61 of you got it right, and 62, 3, so 65 of you did not. But yeah, this is one of the harder points in as far as conceptual topics go in the class. They sound kind of similar, the false positive and the false negative, the type 1 and type 2 error. They sound kind of similar, and it's easy to get them mixed up. So during week 10, when we do our review and our statistical inference catch-all, we'll kind of hit this over, talk about this in greater detail, okay? Yeah. The conclusion was not to reject the null here. Okay, let's continue on here. And so what we've learned so far, okay, so far we have covered a hypothesis test for categorical data or proportions with one sample, okay? And so the topic I'm going to cover now will be hypothesis tests for categorical data with 2 samples. Okay, and so the big picture that we have here is that we have 2 populations. We've got population 1, okay, and then we have population 2. Okay, and you have sample 1, and from population 2 you draw sample 2. Oops, it's hard drawing circles. Okay, and in our populations we have basically some proportion P1 and some proportion P2. This is how our categorical variable is distributed in the population. We've got proportions P1 and P2, okay? And sample 1, you would get sample size N1 and X1 successes. And sample 2, you have N2 and X2 successes, okay? And when you do X1 divided by N1, you can get P hat 1, and from sample 2, you would have P hat 2. And so the question is that, you know, if our samples, or if, our sample proportions p hat 1 and p hat 2, sample proportions p hat 1 and p hat 2 are different, okay, does that mean the respective populations have different proportions? That is to say, P1 and P2 are different. Okay? Or could P1 and P2 be the same, and our p hats were different just because of random chance? Okay, so this is effectively the question that we're asking now when we are doing hypothesis tests with two samples. Okay, we're just saying, hey, we got sample 1 from population 1, sample 2 from population 2. Our two samples have different proportions, right? This sample 1 has 25% this, and sample 2 has 28% this. Does that mean the respective populations have different proportions? Or could my 25 and 28% be just a result of the random chance sampling? Okay, and so a lot of factors come in. You know, how big were your samples and all of this other stuff, and that's so we will do the. I'll show you how to do the calculations to answer this. But this is kind of the question. Okay. Whereas when it was just one sample, we said, could the population have some preset value, some P0 value, and my sample just ended up different because of random chance? That was kind of the question there. Okay, so we can kind of do the same 4 steps as far as hypothesis testing goes, but in this case for 2 samples. Okay, so if you recall our steps, step 1 would be create our hypotheses. Hypotheses. Okay, so our null hypothesis, because we're talking about 2 populations and their proportions, our null hypothesis is always going to be P1 is equal to P2. Okay. So whereas before, when you had one population or one sample, it was, you know, P is equal to some number, and that number depended on what the question was asking. Here, our null hypothesis is always going to be P1 equal to P2. Okay. Alternatively, it can also be written the same. This is the exact same null hypothesis, but we just moved some terms around, and we can also write it this way: P1 minus P2 is equal to 0. Okay. But here, all I did was just subtract P2 from both sides, and we have this. Okay. But I hope you guys can see that these say the exact same thing. Okay. So our null hypothesis can be written this way, and you know, different texts or even the same textbook will present null hypotheses in both forms here. And then the alternative, identical to the null hypothesis, except the equal sign is replaced with something else. So it could be that, or P1 is greater than P2, or P1 is less than P2. Okay. Also can be written as P1 minus P2 is not equal to 0 or greater than 0 or less than 0. Okay, so these are all equivalent to each other. Okay, step 2 being our check, kind of the preparation step. You're going to check the conditions, same as before. Check conditions, except now you have 2 samples and 2 populations, so you kind of have to make sure that n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10 for both samples. Okay. So basically at least 10 successes and 10 failures for both samples. Okay. Or et cetera, et cetera, et cetera. Okay? And then again, choose alpha, choose or identify alpha. And again, if no alpha is provided, use alpha equal to 5%. That's kind of our default value for alpha. Okay, and let's go on here, I hope. All right, okay, so step 3, we do our calculations, okay? Okay, so the calculations, as far as kind of their steps go, are the same steps, it's just the formulas have changed here, okay? So step 3a, I'm going to break into 2 parts. So I've got 3a1. Before step 3a was determining your standard error, and that's still part of our standard error step, but we have to first get the overall p-hat. Okay, so in order to get our standard error, we need to find the overall p-hat, so the overall proportion. And that's going to be your total number of successes, x1 plus x2, and you're going to divide that by your total number of observations, n1 plus n2. So this is the overall proportion. Okay, and so once you figure that out, now you can get your standard error. Standard error is just this formula. It's a little bit ugly. There's not really anything I can do about that. These are the rules here. Okay, so it's p hat times 1 minus p hat times 1 over n1 plus 1 over n2. And the p hat that you calculated as your overall p hat is the p hat that you use here. Okay, so you're use the overall p hat. Okay, so then once you have your standard error, then you get your test statistic. Test statistic z, which is always our kind of the reality versus the expectation. So we have the observed minus the expected divided by our standard error. Okay, so if we think back to what our null hypothesis was or is, our null hypothesis can be written as p1 minus p2 equal to 0. Okay, so this is what we are hypothesizing. We are hypothesizing that p1 minus p2 is equal to 0. So our observed value here the observed is going to be the difference between p hat 1 and p hat 2. The observed difference in our data is the difference p hat 1 and p hat 2. Okay? If the null hypothesis were true, what would we expect this value to be? We expect p hat 1 minus p hat 2 to be 0. I think people are whispering it. So we're expecting it to be 0, right? Okay, so then when we do our z calculation, we would have z is equal, our observed is p hat 1, p hat 1 minus p hat 2. This is what we observed, okay? What we're expecting is a minus 0, okay? But it feels kind of silly for me to write minus 0, so I can just erase that off, okay? But I mean, if you want to put that there, you can put that there, okay? But we got p hat 1 minus p hat 2 divided by the standard error. I mean, if you wanted to put minus 0, you can, because you're subtracting off the expected, but I don't know. You can, because it's minus 0, it's like it doesn't really matter, right? Okay, so our z star, or our z, our test statistic z, is p hat 1 minus p hat 2 divided by our standard error. This is our test statistic. Okay. Okay. After you get your test statistic, what do? Okay, you look up z to get a p-value, right? Okay. And so these are the same rules as before. If the alternative has greater than sign, then the p-value is the area to the right of z. If the alternative has a less than sign, the p-value is the area to the left of z, okay? And if the alternative has a not equal sign, then the p-value is 2 times the tail area. Okay, and so I think this part is all kind of familiar to us, I hope. Okay, and then I'm kind of running out of space here, but I'll just cram it in this little corner. Last step is your conclusion, right? Step 4 is the conclusion, where if p-value is less than alpha, we reject the null hypothesis. And if the p-value is greater than alpha, do not reject the null hypothesis. All right. Good. All right. Okay. Let's. We'll do an example here. This example, I'm going to just. It's just a silly example that maybe plays on stereotypes, but I hope not offensive in any way here. Okay. All right. So the question is. Are people from Texas more likely to own a truck than people from California? Okay. So, okay. So I'm just going to make up data here fitting our preconceived notions of what Texas and California look like. But anyway, okay, so we're just going to go with this. And all right, so let's think of what our hypotheses should be. Okay, so let's say we're going to call population 1. So you got to label these, right? So population 1 we will say is Texas, and population 2 will be California. Okay. And so if we say population 1 is Texas and population 2 is California, and you know P1 would be the proportion in Texas that own a truck. Okay, so P1 is, you know, proportion of Texas that owns a truck. Okay, so let's decide what our null and alternative hypotheses would be. Okay, so our null hypothesis, what do we want to write? We want to say that the proportions of those people, proportions of Texans who own trucks and proportions of Californians who own trucks are equal, right? Or that there is no difference. So we could say P1 is equal to P2. Okay. And then the alternative, the question here is, are people from Texas more likely to own a truck than people from California? So here we would say the alternative should be P1 is greater than P2. Okay, so we have basically a one-sided test, and when it comes down to getting our p-value, we're going to take the area to the right of the z-score, okay, because of the way our alternative is written. Okay, so we will check conditions here for step 2. So as far as checking conditions go, we'll have to look at our data. Okay, so our data consists of sample 1 from Texas and sample 2 from California. Okay, and then we will say these are random samples. Okay, all right, so I'm just going to make up numbers here. Let's say we surveyed 110 people from Texas, and 55 of them own trucks. And in sample 2, we surveyed 105 people from California, and 30 of them own trucks. Okay, so you know, random. Sure, that's met. Okay, large sample. Large sample condition. We want to make sure Texas has at least 10 successes and 10 failures, so that's good. Texas at least 10 successes and 10 failures. And then California also has at least 10 successes and 10 failures, right? We got 30 people owning trucks, and that means what, 75 that don't, 55 who do, and 55 who don't in Texas. So we've got at least 10 there. Okay, and then large population. Yeah, we're looking at Texas and we're looking at California. Those both have large populations, right? Like our sample size is 110. 110 times 1,000 times 10 is like 1,000, and there's more than 1,000 people in Texas and California. There's like, it's the two biggest states in the union. So we got more people in California than the entire country of Canada. So what? For real? Yeah. So yeah, if people move to Canada, then like that's like a lot of people. Okay. All right. Okay, so let's do our calculations now. Okay, so let's get our overall p hat. What is p hat? So actually, let me flip back a slide and just copy our data. Okay, just so I have this. Okay, so I'm going to put our data up over here. Okay, so our p hat is x1 plus x2 over n1 plus n2. Okay, so the total number of people who own trucks is 55 plus 30. We have a total of 85 people who own trucks, and we're going to divide by the total number of people we surveyed, which is going to be 215. So our total overall proportion is 85 divided by 215. That's not helpful, calculator. Okay, so 85 divided by 215, 0.3953, okay? This is my p hat. Okay, and then for our standard error calculation, we're going to do p hat times 1 minus p hat times 1 over n1 plus 1 over n2. Okay, so what is this? 0.3953 times 1 minus 0.3953 times 1 over 110 plus 1 over 105. Okay, so when I punch this into the calculator, because I already have 0.3953, 4888, whatever, typed in or already on the screen, I'm going to just hit the answer key. So that replaces the 0.3953. I'm going to hit answer times parentheses 1 minus the answer times parentheses 1 over 110 plus 1 over 105. I'm going to close that off, hit equals, and take the square root of this number, and I get 0.0667. Okay, so this is my standard error. My test statistic z would be our observed minus the expected divided by our standard error. So our observed difference is p hat 1 minus p hat 2 minus the expected difference of 0, so I'm just leaving that off, divided by our standard error. Okay, so our p hat 1 is 55 over 110. P hat 1 is 0.5. And p hat 2 is 30 divided by 105. That's like, I don't know, that's something else, okay? So, I mean, because I've got a calculator, I don't even have to crunch these out. I mean, because it's just a proportion, I could just type in 55 over 110, which I know is 0.5, and 30 divided by 105. Okay, I could just punch it in this way, divided by my standard error, which is already in the calculator. So that's what I'm going to do. I'm going to just do 55 divided by 110 minus 30 divided by 105. I'm going to close that off the parentheses on the top, and I'm going to just hit divide, and then my standard error 0.0667 is already in there, so I'm going to just say divide by the answer key there. Okay, and I get 3.2123, so I get a z-score of 3.21. So far, so good? Okay, great. All right, and then so we have z equal to 3.21. So what does that mean? Well, it means under the null hypothesis, we are expecting a difference of 0 percentage points, right? But what we observed is what we observed is 0.5 minus, so I think p hat 1 was 0.5 and p hat 2, if you do like 30 over 105, I think that ends up being like 0.286. We end up observing a difference of basically about 21 percentage points, okay? So our observed difference is 0.214, which is equivalent to z equal to 3.21 standard deviations away from the mean, okay? So we're pretty far away from the mean as far as z-scores go, okay? We're over 3 standard errors away from the mean. So it's unlikely that our thing happened by random chance. We can get the p-value, so because the alternative has a greater than sign, our p-value is the area to the right of z equal to 3.21. Okay, so if I pull up my z table here, 3.21 corresponds to an area of 0.9993. And so the area to the right of that is 1 minus 0.9993, 0.0007. So my p-value is equal to 0.0007. Okay. All right, so if alpha is 5%, this means our p-value is less than alpha. Okay, and so that means it is unlikely for our data to be a result of just random chance. A result of just random chance where we assume P1 is equal to P2. Okay, so therefore we reject the null hypothesis. Okay, we conclude that the proportion of Texas that owns trucks is higher than the proportion of California that owns trucks. Okay. I hope that's all right. Any questions here? We're good? Okay. You know what? We'll just do a freebie clicker thing. Just everybody, I'll start this. Everybody just click A on the everybody click A on the clicker, and we'll give you a point here. Wait, somebody clicked a B. Oh, no. Okay, we're good. So everybody just click A. A as an apple, not... Someone clicked a E as an elephant. Someone's just messing with me here. I promise. I see it bouncing around here. Okay, so just click that. That's it for this week. Have a great weekend, you guys. We'll see you guys next week. Just 2 more weeks of school. So good luck, everybody. All right.